Yes. Symbols for me. What do you want to use? X big D. Do we have to use an X? Yes, we have to use an X because we're saying it's excellent. Excellent, Karina. Thank you for that one. So we want to do, let's say we have an X. Actually, let me give you credit for having done that. X. So you said X big D. What do you want that to be? Normal or disease? So normal, dominant or recessive? Dominant. All right, cool. And then another symbol? X little d, and that's disease and recessive. Any more symbols we need? And Y. Does that get a little d or a big D on it? Karina? None, exactly. Because it's got no gene for this on it. All right, cool. Thank you. So let me call another name, and we'll start with some genotypes. Anam. Anam, are you here? Anam. Yes. So, anybody you like? The tip-top parents? All right. And what are they? What's the dad? So he's got to be XY. Actually, thank you. So he's XY. What's on his X? Big D or little d? What's he got to be? He's got to be big D because he's normal. The guys you know right off the bat. And mom's got to be XX. What do you know before you know anything about who she's related to? What do you know just by looking at her phenotype? What's one of her X's got to be? She's got to have a big D because she's normal, right? What do you know about her other X? It's got to be little d. Why? Because she has an affected son. All right. So we're rolling. This guy here's got to be what? X, little d, what? Y. All right. And the sister, well, she's got to be X big D, and she's got to be X something. What do we know? It has to be X big, X big. Does it have to be X big, X big? Not necessarily. Because look, she's got to get an X big D from dad, otherwise she wouldn't be a she. But she could get either flavor of X from mom. So she's an X big D blank. All right? Let's see. What about her over here? She's an X what? Big D, X, blank. We don't know. This daughter down here, X big D, because she's not affected, X what? Do we know for sure little d? I hear yeses, I hear no's. All right, let's think this through. What does she get? What she has to have got from her dad? She has to get an X little d from dad, because if she got the Y from dad, she wouldn't be a she. So she's got to be X little d. Likewise, X big, X little. He's got to be X what? Big DY, he's unaffected. And X little dy, is that possible? Can those parents have an affected son? Yes. X, and this is going to be X big dy, is that possible? Yes. So it's possible that SLR, all right, big E, how many people had to bring in a disease allele? I got one. I got just one. Or two. Because maybe somebody else could have brought it in. What's the minimum number required? One. And who is that one? The mom, way at the top. Right. So, there's only one. One unrelated carrier. Therefore, I'll say at the bottom, it can be autosomal recessive or SLR. Most likely, SLR. So that's why we do these unrelated carrier thing, right? Sometimes when you do it, it can only be one. Sometimes it can be more than one. How do you decide? You do this unrelated carrier business. So, on an exam, you have to read carefully. If I ask, is it possible that this is sex-linked recessive? You would say yes. If I say, is it possible that it's autosomal recessive? You would say yes. If I said, is it possible that it's autosomal dominant? You would say no. Okay. If I said to you, what is the most likely mode of inheritance? You would say sex-linked recessive. All right. So it depends on the question I asked. Okay. Questions about that and the unrelated carriers and all that business before we go a little further. Why is sex-linked the more likely one? Because people like grandma up there are rare. People with little d's in general are rare in the population. 1 in 1,000, 1 in 10,000. So you only need one rare person to make this work. The other, if you tried autosomal recessive, you had to get 3 of these rare people. Both grandparents and one of those uncles had to be carriers. And carriers are rare, so it's unlikely you'd find 3. It's more likely you find 1 rare person than 3 rare people. That's the idea. The one with the fewer rare people is more likely. Right. Yeah. Can the Y chromosome carry any disease? In Bio 111, no. The world is a very interesting and cool place. It turns out, yes, there are certain, like hairy earlobes or something like that is like some weird thing that is on the Y chromosome. And there's some male sterility genes on the Y. But we won't worry about them. But there are a few. There's not a lot of genes on Y, it turns out. All right. Very well. What I want to segue to is a little bit a somewhat related thing that's important for thinking about pedigrees and the like. There are times you'd like to know how likely something is. In fact, some of you may go on to be genetic counselors. If you are doctors, you may have to provide genetic counseling to your patients. So one of the issues they have is, what is the chance, given my family history, that I will have a child with a disease, with a particular disease? Okay? And so you need to be able to assess that, not just say, does the pedigree work this way, but what is the chance of a diseased child, for example? So I want to talk a little bit about that. So probability, just to be very rigorous about this, sometimes you write abbreviated P, is the chance, or the likelihood, that something will happen. And probabilities range from P equals 0 to P equals 1. And this is, it certainly won't happen, and it certainly will, right? And in real life, there are, I guess, the only 2 events with probability 1 are death and taxes, as they say. Other than that, everything has a slightly lower probability than 1. I suppose there are some things with probability 0, but we don't have to discuss them right now. And as a reminder, if the probability is 3/4, then in a large number of trials, it will happen 3 times out of 4. And this is huge, all right, that this large number of trials matters, right? It's the Foxwoods syndrome, right? That I could walk in and pull a lever on the slot machine and win $1,000. It's not particularly likely, but the single event oftentimes appears to violate the rules of probability. A small sample size can be skewed. A large sample size, which is what Foxwoods depends on a large sample size, they win. Right? On average, they win. And so probability is 3/4 that something will happen. Doesn't mean if I do it 4 times, I get 3 out of 4. It means if I do it 4,000 times, I get it 3,000 about. But it's never going to be exact. And the larger the sample, the more closely it's approximated. If you think about it again, if you flip a coin twice in a row, you might get, or even 5 times in a row, you might get 5 heads in a row. That's unlikely, but it's possible, even though the chance is 50-50. All right. So there's a rule about probabilities that the probability of A and B is equal to the probability of A times the probability of B. So there's lots of different examples you can think of. If the chance of rolling a 6 on the dice is 1 in 6, and the chance of flipping heads on the coin is 1 in 2, the chance of rolling a dice and getting a 6 and flipping a coin and getting heads is 1/6 times a half, or 1/12. Okay? So when you have two things, X, something and something else, then you multiply. When it's something or something else, it's actually a little more complicated. The simplest case in probability is if you require both to happen, the chance of it happening is the product of those two. So let me give you a nice concrete for instance. Suppose we have an autosomal recessive disease. Just sort of classic example. Big D is normal and dominant. Little d is disease and recessive as usual. All right. Suppose we have a family, and I'll just give all the genotypes, big, little, and they have a little daughter, and they have a son, and he's big D, question mark, or I should use the official name, he's big D, little d, or big D, big D. And the question is, if he marries an affected female, little d, what is the chance that their child will be little d, right? So we have parents, grandparents, are carriers. The aunt is definitely affected, and the wife is affected, right? What's the chance that that couple will have an affected child? Okay. So it depends on two things. Two things have to be true. Dad has to be a carrier, and Dad has to pass his disease allele down. And so since both of those have to be true, that and that, it's the product of those probabilities. So let me show you how you do the probability there. So to have a little d kid, Dad must be big D, little d. We'll call that event A. And he must give his little d to the kid. And we'll call that event B. Right? So let's do some analysis. So the probability of A is the chance that the dad is a carrier. Okay? So how do we figure that out? Let me do it this. Sorry, I'll do it that way. There you go. Chance that dad is a carrier. So let's draw up the old Punnett square. Right. Big D, little d, big D, little d, big, big, little, little. All right? You might be tempted to say that the chance that dad is a carrier is 1/2, because half of those squares are big D, little d. Turns out it's not. Why do we know there's one of those four possibilities we can rule out. We know that dad is one of there's one of those squares that dad can't be. He can't be little d. Why can't he be little d? Because up there he's not colored in. We know he's normal, right? So what that means is dad is a carrier given he's not disease. Right? That means we only care about these three boxes. Therefore, in this case, there's 3 ways to be unaffected. Of those, 2 are carriers. That is big D, little d. Therefore, the probability that dad's a carrier is 2/3. Right? This is a little bit weird, but if you think about it carefully, given we knew nothing about dad, right? You never met him, you didn't have his box as a question mark. there's a 50-50 chance he's a carrier, given his parents are both carriers. Since you know he's not diseased, you can exclude that box. So there's only 3 possibilities for Dad, of which 2 are carriers. So there's a 2/3 chance that he's a carrier, given that he's not diseased. Of course, it's about that little bit of analysis before we go one step further. It's a little bit weird way to think about things, but it's actually quite important. Yeah? I'm talking about this. I'm talking about this individual, this guy. To be really clear, it's this Dad, that guy. Right? That's that guy. Right? Yeah. Because that man's parents are both big D, little d. So we're trying to understand about the dad in this family, this individual here. So let's do the other half. Probability of B is 1/2. That is the chance that a carrier gives a little d to a child. Therefore, the probability that the child will be little d is going to be 2/3 times 1/2 is equal to 1/3. All right? So what that means is, on average, in lots of families, you have many families like this, on average, you'd expect 1/3 of the children to be affected. In real life, the dad is either a carrier or he isn't, and then have a 50-50 chance. But on average, sort of in a public health point of view, what do you tell people in general in this? You say they have a relatively high risk of having affected kids. Okay. Once they start having kids, you might know. If they have kids and one of them is affected, then you know the dad's a carrier. But until that, that's the risk. Questions about that? All right.